Okay, we are back and better than ever. Are you ready for Vectors in Space Part 2? Okay, I'll stop. All right. The vector between 2 points. Like I said in the previous video, nice thing about vectors in space and 3D space is that the rules are the same as in 2 space. No big whoop at all. So if I want to find the components of a vector, of the vector between 2 points in space, I just subtract the corresponding components of each vector, the second point minus the first point, or the termination point minus the starting point of the vector. So x2 minus x1, y2 minus y1, and z2 minus z1. And if I want to find the distance between those vectors, it's the distance formula really. It's a square root of the difference of those two vectors squared, and you take the sum of all of that. I didn't say that very well, but you can see it right there. Very simple, very easy. Okay, so we're going to do all this. If P is negative 3, 1, 2, and Q is 1, negative 1, 3, find the vector OP. Well, remember, O means the origin, and the origin has coordinates 0, 0, 0. So clearly, vector OP is going to equal negative 3 minus 0 is negative 3. 1 minus 0 is 1. 2 minus 0 is 2. That's in component form. In unit vector form, that would be negative 3i plus 1j. We don't write the 1, please. Plus 2k with the unit vectors I, j, and k. Okay, so that was A. Let's do B. PQ is going to equal, and we're just going to do this in our heads. 1 minus a negative 3 is 4. Negative 1 minus 1 is a negative 2. And 3 minus 2 is 1. That is in component form. In unit vector form, that would be 4i minus 2j. Oh, that makes me hungry. Plus k. Okay, and then part C is simply going to be the magnitude of vector PQ. It's just the square root of the sum of the squares of the components. So that's going to be 4 squared plus a negative 2 squared plus 1 squared. What's that? Square root of 16, square root of 21, I think. I hope that's right. Of course it's right because I am me and you are not. Okay. Next slide. Cruising through here. Vector equality, same thing as in 2Ds. Two vectors are equal if they have the same magnitude and direction. The components are going to be the same. If A and B do not coincide, know what coincide means? That means if they are not on, well, coincide means the vectors would be on top of one another or the same vector. Then they are opposite sides of a parallelogram and lie in the same plane. Great. So let's do a problem like that. We have ABCD is a parallelogram. A has the points negative 1, 2, 1. B is 2, 0, negative 1. They skip C, that's important. And then D is 3, 1, 4. So, I mean, if you just draw some parallelogram in 2D, A, B, C, and D, very important to realize that AB is going to be parallel to CD. And of course AD would be parallel to BC. Okay. No different in 3 space, maybe a little bit harder to get our heads around. So I used the 3D plotter that I showed you before, and I plotted those points. A, negative 1, 2, 1. B, 2, 0, 1. C is what they're asking us to find, and then D has the coordinates 3, 1, 4. Well, if you look at these points, you might think, well, how do you know the point isn't over here where my cursor is right now? Well, if I name a parallelogram A, B, C, D, they have to go in that same order once a direction is established. That means C has got to be here, and because D is here. Okay. Well, if this is indeed a parallelogram, I know that AD must be parallel to BC. Well, if that's the case, then AD must be equal to BC in vector speak. So let's first find the vector AD in component form. So the vector, the vector AD would equal, let's see, 4, 3 minus a negative 1. 1 minus 2 is negative 1. And 4 minus 1 is 3. Okay, so we know that if they're parallel, they're going in the same direction. They're also equal in length. So we know that BC must be equal to AD. Okay, well, BC, let's find out what vector BC is equal to. That's going to be equal to A minus 2, B minus 0, so that's just B, and then C minus 1. That is a 1, isn't it? Oh, it's a negative 1. Okay, we just can't see it. I need to put negative 1 in there. So C minus a negative 1 is C plus 1. Okay, so if BC equals AD, then that means that A minus 2 must equal 4, which implies that A equals 6, and that B minus a negative, or that B equals negative 1, sorry. Okay, clearly. And then C plus 1 must be equal to 3, which means that C is equal to 2. Which means that the point C has coordinates 6, negative 1, and 2. 6, negative 1, and 2. Okay. And, well, let me show you what that looks like, because I did plot the final vector. Here's the drawing that we did, and I plotted the point 6, negative 1, 2 right there for you, and you can see that it is a parallelogram. Okay, that's it, and we will see you next time.